As my partner Gustavo mentioned, I'm gonna be continuing with the presentation and we're gonna be starting with the second validation, which is the electrical components connection. We had that we must be able to detect obstacles to a range to around 3 to 7 feet. The sensor should cover an angular position between 15 to 45 degrees. The system must have a response time of at least 2 seconds and it should provide a buzzer signal to alert the patient. Our objective of this experiment is to validate the performance of the required technology. One safety precaution we made is an open space. The procedure is an evaluation will be performed with a series of tests using different obstacles to ensure the detection range. Ensure that the sensor can detect movement in any direction. The equipment will be the smart cane, the obstacle, blindfold, and a volunteer. For the first two MOPs, we have that it must be able to detect obstacles to a range of 3 to 7 feet. As you can see here on figure 30, we have a simulation of the smart cane detecting obstacles with its buzzer and its vibrating motor activating. You can see it's approaching the mark of 3 feet. It detects the obstacle, it vibrates, the buzzer sounds, and the LED light it's turned on. For the figure 39, we can see that the smart cane it detects the obstacle at a range of around 4 feet, alarming the patient with its buzzer. For the other two MOPs, we have that the sensor should cover an angular position between 15 to 45 degrees. Here on figure 32, we can see the volunteer testing the smart cane with an angular position of 30 degrees, and the system must have a time response of at least 2 seconds. On figure 31, we have that the time response is 1.25 seconds. Here is another video on figure 33 of all the control system, making sure it detects the alarm goes on, the vibrator motor turns on, indicating the patient that it's obstacle in its way. Here on figure 34, we can see another picture of the LED light turning on, detecting obstacles in the middle for the patient. Under third validation, we have the structural housing and handle grip design. We have that we must have all electrical components covered. We must accommodate for all electronics components in handle and housing case. We must enhance the system availability by reducing sharp edges and improper bends, resulting in a safe wire route. The structure should be cylindrical and ergonomical shape and must comply non-harmful material to the environment. Our objective is to ensure the security of all electrical components in a safe wire routing to operate successfully. For the procedure, we must validate all components in the correct location inside the handle and housing case covered with wires with wire assembly. Evaluate the structural design involving its shape and materials. The equipment is the electrical and the structural components. For the first MOP, we have that we must have all electrical components covered, must accommodate for all electrical components in handle and housing, and we must enhance the system availability by reducing sharp edges and improper bends. On figure 35, we can see we have all electrical components covered with its proper housing and lid. On figure 36, we can see the accommodation of the electrical components and its wire routing. And on figure 37, we can see the electrical components covered and the sensor activated with its LED light on. For the system validation, the structural and handling grip design, we imported a CAD format into Creo and SolidWorks to a software to prepare for printing. The name of the printer was the Prusa. We configured the measurement, especially thickness, and if needed, we added some support. We printed on the Prusa E3 MK2 3D printer at the biomedical engineering facilities at the University Polytechnic of Puerto Rico. On figure 38, we can see the first layering of the material for the housing. We can see a better picture on figure 39, and on figure 40, we can see the housing lid. Um, for the other two MOPs, we have that it should be cylindrical and ergonomical shape and must comply with non-harmful material to the environment. Following the result that we obtained, the structural design of the housing case was based on an ergonomic shape, and the PLA material used on the 3D printer is classified as biodegradable material, making it non-harmful to the environment. You can see on figure 41, this is the final structure of the housing case, and on figure 42, the final design of the housing lid. Here we have on figure 43 that the cap and handle print, that which is the where the vibrating motors are gonna be, and on the figure 44 we have the final design for the cap plus the handle, which it goes into the cap goes into the handle. On the validation number 4, we have that the battery access. The location of the battery should be easy to access, and the device should last at least 8 hours before recharging battery. Our objective is to identify that the smart cane utilizes a proper rechargeable battery, resulting in 8 hours of battery lives. For safety precaution, we wear gloves and safety goggles. The procedure is to evaluate battery life, assuring that the system is on during 8 hours to get the expected results. Equipment, we had the battery and the handle grip. Uh, you can see I mentioned that the location of the battery should be easy to access and the device shall last 8 hours before recharging. We following the result we obtained. The battery was easy to access by disconnecting the handle grip from the housing case, as you can see on figure 45. This is the location of the battery. And the performance test of the battery life was successfully accomplished by letting the device on for a period of around 8 to 10 hours to determine an accurate battery lifetime. On the other validation, we have that it must reduce injuries in patients that suffer from visually impaired and blindness in a 40%. The objective is to complete an all evaluation for patients reducing injuries that suffer from visual impairment and blindness, reducing in a 40%. The procedure is the difference between the percentage formula would be used to calculate the percentage of reduction using meter values. We have the equation 1 is distance 1 minus distance 2 divided into distance 1 plus distance 2 divided into 2 times 100%. That equals the reduced injury percentage. So we have that the distance 1 is 1 feet, which is the simulation of distance range with device, and that our distance 2 is 4 feet, which is the validation of distance range with device. Since the simulation of the analysis in software was 1 feet, the physical test was taken into consideration with an expected data of 4 feet and 2.8 feet, which is the vibrator activated. Once we apply the known values on the formula, we have a percentage of reduction of 30%. Entering in what's going to be our MOP validation summary, we have the first one, which is we must accommodate the vibration frequencies set to around 130 to 200 hertz. It was the vibration frequency is set to 200 hertz. The device should be able to complete risk of 1.5 to 2 of safety factor. Our safety factor was 1.9. The system must attend a load analysis of structural mechanisms. We can see we have the equivalent stress and the deformation. On the all controlled components should not exceed 1.5 pounds. We have that the components weighted 0.2434 pounds. The structural weight should be less than 2 pounds, which our structural weight was 0.6693 pounds, and the overall cane should weigh less than 3 pounds, and our weight cane was 0.9304 pounds. For the seventh, we have that we must be able to detect of a range of around 3 to 7 feet. Our detection range was about 4 feet. On the next one, we have that the sensor should cover an angular position of 15 to 45. The angular position was set to 30 degrees. The system must have a time response of at least 2 seconds. Our time response was 1.25 seconds. It should provide a signal to alert the patient. It passed, as you saw in the videos. Must have all electrical components covered. It passed, as you saw in the photos. We must accommodate all components into the housing case. You saw in the same photo as the previous MOP. We must enhance the system by reducing sharp edges and improper bends, resulting in a safe wire rad. Is passed. Also was shown on the photos. The electrical should be cylindrical. The structure should be cylindrical and ergonomical shape. It also passed. For the last four, we have that we must comply with non-harmful material to the environment. As I mentioned, the PLA material, which was the one used for the all the 3D printer, is biodegradable material, so it's non-harmful to the environment. The location of the battery should be easy to access. As you saw in the pictures, it's very easy to access. You just remove the handle and you can access the battery really fast. The device should last at least 8 hours before recharging battery. It passed, and we must reduce injuries in patients that suffer from visual impairment, reducing it 40%. As you saw, we reduced it by a 30%. For the overall project conclusion, the goal for the electrical sensor white cane is to bring a product up to technology modernity while maintaining its affordable price and reducing injuries in patients that suffer from visual impediment and blindness, reducing a 40%. The validation reveals that the patient injuries can be controlled by providing a smart cane with ultrasonic sensors that vibrate motors, reducing injuries by 30%. The results prove that the electrical sensor white cane reaches its goal and satisfies the needs of its users. This cane is generated towards an elderly demographic group that will demand comfort, accessibility, and affordability for the product. Using the ultrasonic sensor, Arduino board, and vibrato motor, the product greatly increased the objective detection range, therefore improving the lives of the blind and visually impaired users. Besides the cane technology improvement, the design was altered to give the users a more comfortable and ergonomical handle. Overall, the smart cane uses of technology and ergonomic design has greatly improved upon the traditional white canes and has taken a great leap towards improving the lives of the visually impaired. For the overall project recommendation, it is important for this research to highlight that the investigation to be used by patients who have the disability of visual impaired to determine a more accurate data, promote an approach between a medical team, patient between all ages in order to improve the electrical sensor white cane system, process on the importance of the project, to determine specific aspiration, allowing an overall analysis and a satisfying product. Performing tests using other types of sensor indicate different distance as long and short mode distance. It is recommended to reduce the weight of the device by a smaller electrical components such as the battery, Arduino, mini breadboard, and cables to develop a smaller and accessible handle grip and housing case for the patient's comfort. That'll be all for this presentation. Thank you for the attention, and for any questions you can contact us via email.